Yeah, great. Right, welcome everyone. So today we have Nicolas Stevens presenting for us. Nicolas is currently a visiting scholar at Harvard University, where he's working with Big Hogan and others on issues related to electricity markets. He is a PhD student at the final stages at the University of UCLouvain in Belgium. He's in the center that's called Center for Operations Research and Econometrics, also known as CORE, and he's working with his advisors at CORE, and that's a very well-known institution in the context of electricity markets and optimization. And Nicolas will be talking to us about how to deal with non-convexities in electricity markets and price clearing, scheduling, and price formation. And if you haven't heard the term convex hull pricing, you'll get to understand what that is during his presentation here. So.
Awesome. Thank you, Odin. Thanks. So thanks for the invitation. I'm super happy to be here to present this research. Yeah, we'll understand that's a bit more dynamical if I'm like that. So I would like to present you this research, which is a joint paper with Anthony Papavasiliou, which is from the National Technical University of Athens, and Yves Smith from UCLouvain in Belgium. And it's mostly based on a paper that we published a few months ago in Energy Economics, and which is titled "On Some Advantages of Convex hull Pricing." And then I added in the title "For the European Electricity Auction." But just to be clear, I think this is also valid, or what I'm going to tell you in the next 45 minutes or 1 hour is valid for, I think, European electricity auction, but also beyond that for US market as well. Okay, so let's get started. Just, I think there are two main motivations for the work that we are doing here. The first motivation is a bit more theoretical. And then the second motivation is mostly based on some policy discussion that there has been in the last 20 years in US electricity markets and in European electricity markets. And I would just like to spend a bit of time in the beginning here to motivate a bit what I'm doing and cover these two different motivations. So let's start with, let's start with the theoretical motivation first. So I think the easiest way to just understand what this is all about is to look at a small example together. So please consider the small market that I've represented on this slide. So it's a market where you have a supply curve that is made of two bids, C and D, and a demand curve made of bids A and B. So you could view that as a small model of an electricity market, or you can also view that more as an auction where some suppliers and consumers submit bids, and then the auctioneer needs to announce what are the cleared quantities and the market clearing price. So if everything here was convex, I guess that most of you would see that the allocation that would optimize the as-bid surplus would be to clear A, and then to clear a part of C, like 90 megawatt on C, and to reject the other bids. And then if you pick a price of 30 euros per megawatt hour, for this price, all the market participants would have the incentive to actually implement the allocation that I've described, right? So you would have an equilibrium. And then the surplus in that hypothetical case would be, this area between supply and demand, so between A and C. Now the question that we are going to be busy with for the next hour is what happens if I just add a tiny constraint on this problem, and I say that now C is indivisible. So C can either produce 0 or it can produce 100, but it cannot produce anything in between. Right. Then you can ask again, okay, what would be the optimal allocation of resources and what would be the market clearing price? Now for the allocation, it's quite straightforward. So when you have this additional constraint, what you would do is you would clear C entirely now because it's indivisible, and then you would still clear A and now a little bit of B as well. And then the surplus would be the area between A and C in light gray minus the area between C and B in dark gray. So somehow to some extent, as far as the surplus is concerned, the impact of adding this indivisible constraint is not dramatic, right? So you have a little less surplus because of that constraint, but nothing too bad. However, where you have a significant difference is that in this case, actually, you cannot find a price anymore that would make everyone happy and make everyone willing to implement this optimal allocation. And I think that's pretty straightforward to see on this example. So if you consider a price of 20 euros, for example, well, at 20 euros, A and B, they are willing to implement that. But C does not want to produce because it would be losing 10 euros for each megawatt hour that it produces. Then if you say, okay, sure, let's take a price of 30 euros. Well, for 30 euros, C would be fine to produce, but it's B that would not like to consume anything because his willingness to pay is only of 20 euros. And so you can turn that problem whatever you want. Like for any price that you would pick, there would be at least one market participant that is upset and does not want to implement the optimal allocation. The way to view it formally in economics would be just using the supply and demand, like plotting the supply and demand correspondences. And if you do that, what you see is that in the supply correspondence, you have this kind of leap, which leads to a supply and demand curve that do not cross, and so you don't have an equilibrium. So that's a little bit for theoretical motivations of what we are doing. And so in the next 45 minutes, what we will see is there some ways, some possible solution to that problem, or some ways to maybe mitigate a bit the issue that we have just seen, which is there is no equilibrium. Okay. Right, yeah, and so I think this problem is interesting. It's also connected with, to some extent, to some more fundamental question in economics about what the price and the market can or cannot do when you have some assumption, when you have some market participant that have features that deviate from classic assumption you make in microeconomics, which is that everything is convex, continuous, and so on. And so, for example, an economist like Albert Scarf that worked on the topic, then simply wrote, yeah, in the presence of indivisibilities in production, the price, they simply don't do the job that they were meant to do. Okay, so that's a bit so for the theoretical motivation. We want to find some ways to solve the problem that I've just described. Now, it turns out that this is also, like, it's not only theoretically interesting or intriguing problem, but it's also something that has been discussed quite a lot in policy discussions around the electricity markets in the US and also in Europe. And so I will just take some minutes, let's check the time, some minutes to just introduce you to what are the policy context of this discussion. So this is a little bit what is the landscape of electricity markets in the US. In this map here, you see the white regions, which more or less correspond to regions where which are still managed, where the electricity sector is still managed as a vertically integrated monopoly. And then the colored region would correspond to places where a market has been implemented. And so you have some ISOs who operate the grid and also run the market. So that's, for example, CAISO in California, ERCOT in Texas, PGM, and so on, right? Now, as far as the problem of pricing non-convexities is concerned, all these colored region, in all these markets, you do have the problem that I've described in the previous slide. So all these markets, they do include some non-convex bids. I guess that most of you would be familiar with the notion of unit commitment problem. So all these markets are basically running some kind of unit commitment problem where the suppliers can submit some multi-part bids that include some operational constraints, some all the cost structure with startup cost and so on. And all these constraints and production function includes non-convexities. And so in the end, the auctioneers here or the ISO need to find some ways to deal with that. Now the timeline here, I'm trying to put some of the main milestones for pricing non-convexities in these markets. So I think it's fair to say that in the early 2000s, the main approach that was implemented by this ISO was to just apply marginal pricing, which works very well in convex settings. And then you just pay side payments to the market participant that are unhappy with the uniform price or that don't have the right incentive to implement the optimal allocation. And then quickly emerged the idea that, yeah, maybe there would be ways to actually improve that. Maybe the side payments sometimes were relatively high and can also result in some bad incentive for the market participant that would then have incentives to self-schedule instead of following the market dispatch. And so very quickly emerged the ideas in the 2000s that there would be maybe a more clever way to do this pricing than just do marginal pricing. And then if you look at the last 10 years here, In 2014, you have the FERC that launched a consultation about price formation in electricity auctions. And that was followed by some proposal of reform by MISO and then by PGM, who implemented something a little bit different than marginal pricing, which is called ELMP. So I think the bottom line of this slide is just to say that, so this problem that you have seen in the previous slides, it's a problem that holds in all these markets in the US. And the way the different auctioneers or ISOs have tried to solve this issue is heterogeneous among ISOs and has been a long-lasting debate for the past 20 years and is still under discussion today. Yes.
Unit commitment is non-convex, but currently it is not all or nothing. That in terms of production, you can commit a power plant, but you don't have to produce, the way that you wanted to produce, like the amount that you wanted to produce. Right, in the previous chart that you showed, like the plot,
Yeah.
it was all or nothing, but in practice, it is not the case, is this?
So I suppose that in unit commitment model, the kind of non-convexity you would have is, for example, that a power plant that can produce up to 400 as a minimum of 100. So then it could produce anything between, let's say, 100 and 400, but it could not produce anything between 0 and 100, right?
Correct, but it doesn't have to produce 400, for example.
Indeed, yeah. So the example in the previous slide is the simplest possible example you can think about, but it's true that the non-convexities are not, they are not all exactly the same way as the one of the first slide. Yes. Yes. But in principle, I mean, you could design the same example as the first slide with what I've just said, where you have a minimum operating limit and maximum operating limit, and you could also find some cases where a price does not support a solution. Yeah. Okay, so that's a little bit for the US. Let me briefly comment on the European, the electricity market landscape in Europe. So the European market is a bit the same story as in the US, although it has also some peculiarities and some differences. So I think that the regulation of the power sector in Europe also took place during the late 90s, early 2000. You have the so-called first, second, and third energy packages, which are packages of European laws that in the end resulted in the liberalization of the power sector. However, one noteworthy difference between Europe and the US is that the institutional arrangement is slightly different. So in the US, you have an ISO, which operates the grid and also runs the market. In Europe, it's a bit different. So you have typically a national TSOs, or transmission system operator, who is in charge of managing the assets of the grid and also operating the grids in real time. And so that's, for example, in France, you have RTE, Elia in Belgium, Red Electrica in Spain, and so on. And then you have the nominated electricity market operators, sometimes called the NEMOs, or power exchanges, that are the one that operates a market, which is a pan-European market. And if you look at this market in particular, I'm again putting some milestones over here. So I think one important milestone is 2006, when there was kind of first European market. It's called the Trilateral Market Coupling. That was coupling France, Belgium, and the Netherlands. And then this one extended to Germany in 2010, so to include the entire CWE region. And then that was further extended in 2014 to, I think it was merged at that time with a market organized in the Nordics. And then also extended to Spain and Italy. And that market for the past 10 years and then has kept extending with some dropouts, unfortunately, from our British friend. But otherwise, it kept extending to more countries in Europe, so that today, this European market covers all the regions I've highlighted in blue here, which is 27 countries, 30 TSOs, 16 NEMOs, and I guess many languages. So a big European project. So
I forgot to mention in my intro that the consulting company you used to work for developed the algorithm that clears the head market, right? Of the entire, of all the new parts there in the map. So that's quite an interesting large-scale optimization problem.
Who clears the market? Is it NEMOs or TSOs?
So I think officially it's a consortium of NEMOs and TSOs. Yeah. In practice, how it works is that the TSO submits some network constraints, So typically the way the network is modeled is much less granular than what you have in the US. So you have only like cross-border lines. So each country would be one bidding zone, and then you have cross-border lines that are modeled. And so the TSO submit this cross-border line constraint, and then for exchange, they collect the bids from all the market participants and then submit these bids. And then they run one big auctions. So yeah, there are multiple for exchange, but they all run one, in the end, they are just collecting inputs to one big auction, which clears the entire European market at once. Yeah.
I guess another difference in terms of like if you are a generator in these markets in the US context, you have to bid for each individual power plant at a specific node in the grid.
Yeah.
Whereas in Europe, in most European countries, you can bid portfolio of your resources.
Yeah, that's correct. So maybe so the non-convexity. So as far as the main subject matter of this talk about how do you price non-convexities, you don't really care what exactly is the source of non-convexities or how it looks like. So in the model that I will show later, you will see it's quite generic, but it's true that so in the US you have more unit commitment type of model. So the non-convexities come from this unit commitment model. Here you have typically more, as Odin said, more portfolio type of bidding. So you don't have unit commitment model, but you still have some bids which include non-convexities, like all or nothing offers or these kind of things. Yeah. All right. So I think I need to be a bit faster. So just to summarize, so the main objective of this work, of course, it was motivated by the theoretical motivation I've presented before. It was also very motivated by the European case in particular. So the market that I've just presented you, the European market, has some pricing rule which is very different from some of the pricing rules they've considered here in the US. And this pricing will actually have some drawbacks. And I don't really have the time to enter into the details of that, but it has several drawbacks. And for these reasons, the European neighbors and other stakeholders have actually undertaken some research to maybe reform these pricing rules very recently. So I'm citing, some reference here of the last 2-3 years published by the consortium between Power Exchange and TSOs. And so we thought, okay, because this is a vivid subject of discussion in Europe, because it has also been debated a lot in the US and it's, to some extent still open, it's maybe a good moment to just try to think a bit about this problem, try to formalize it, list what are the possible solutions that have been proposed in the literature, and try to compare these different pricing solutions to weigh the pros and cons of each of them. And so the way I propose to do it, so the agenda for the next 30 minutes is I'm going to try to show you a theoretical framework to establish some concepts that I think are important to think through this problem. And then in the paper, we have a rather theoretical comparison. Here I will skip this theory and go directly into the numerical simulations, where we will see directly how some pricing scheme compares on real auction datasets. All right. So I think we basically need mainly 2 different concepts to get started with that. And the best way to introduce this concept, I think, is using a small toy example again. I promise this is the last toy example of the slide, and it's just a slightly more elaborated version of the example of the first slide. So you have a demand curve with 2 bids A and B, and your supply curve now has 3 bids instead of 2, so you have C, D, and E. C and D are indivisible, and you can compute the optimal allocation. That would be to clear A bit of B, and to clear D. So in this case, you reject C, although it's less expensive, but you reject it because of this indivisible constraint, which means if you would accept it, you would need to clear 200 megawatts. And so considering that, it's more economical to just clear D, okay? Now, mathematically, this would be your primal problem, right? So you just write an optimization problem, which is, I want to maximize the surplus of my market. In this case here, yeah, I've been a bit lazy, so I just copy paste the equations from the paper. So in the paper, we assume inelastic demand. So we just minimize the cost. But that would be the same story with elastic demand. You would just maximize the surplus instead of minimizing the cost, okay? So that would be, so the way to compute this allocation would be to run a mathematical problem like that. You minimize the cost, subject to a market clearing constraint, where you say that supply equal demand, or here supply minus demand equal the net position of your node. And then your net position, so the flows on the network here, should satisfy some network constraints, which is just an abstract set F here. this set of constraints is convex. It's in fact linear in our simulations. And in the European market, that would be linear. In the US, I think in most markets, that's also a linear model. And then your suppliers have some production sets constraints, which are just the set X, J here. And this set is eventually non-convex. And whether the non-convexities are unit commitment model or something else does not really matter for what I'm going to tell you. It's just a production set which include non-convexity. Right, so that's your optimal solution, the solution of your primary problem. And then you want to find some price for that. Now, in this example here, I think there are mainly 3 different prices that you would like to investigate a bit more. So what we want to do here really is, on the first slide, we've seen there is no equilibrium, and there is still no equilibrium here, but maybe what you want to do is to put just the numbers on this absence of equilibrium, like how far we stand from an equilibrium, how bad we are. And maybe some prices, even if they are not equilibrium, are relatively better than other prices when you measure this thing, okay? So you have these 3 prices here. If you consider a price of 15 euro, it's not an equilibrium, but more precisely, what happened is that D here would be losing money, right? When it produces for that price, it would be losing 10 euro for each megawatt hour we produce. So you would have a revenue shortfall of 1,000 euro. Then if you look at the other market participants, you also have B, which is actually upset here for a slightly different reason. So B is not losing money, but he is asked to consume only 10 megawatts, while his willingness to pay is 20 euros and the price is 15. So he's not losing money, but actually he would like to consume more, right? So when you ask him to consume only 10, you're asking him to refrain from consuming, while he would very much like to consume 20 megawatts instead of 10. Okay. So B is not losing money, but he has a lost opportunity of 50 euros. Okay. And you can do this exercise for the other prices for 20 euros or 25 euros. So for 20 euros, you will see that D that has a revenue shortfall, but it's a bit lower. Now it's only 500 euros. B is fine, but now it's C that has some lost opportunities of 1,000 euros. And then if you go to 25 euros per megawatt hour, D has no more revenue shortfall. But it's B now that is losing money because the price is higher than his willingness to pay. And C has a lost opportunity, which is even higher. Okay.
Where do we account for the like load shedding in your formulation? Because here you have load shedding, right? Like he doesn't get whatever he wants. Like you don't serve like the
yes,
customer B.
Yes, so I think B here, it could be viewed simply as, as a consumer, you want to consume that much. He has a load shedding, but it's not a forced load curtailment, right? It would be voluntary given some price.
Let's assume that consumers respond to prices voluntarily, basically.
Yeah.
Sorry, just for clarification. So now you assume that C and D is invisible to the market, right?
That C and D, what?
C and D is invisible to the market.
They're indivisible, yes.
Sorry, indivisible. So, so what's your solution? Solution is to find a way to make C and D visible to the market, or you are trying to see we can shift the kind of the demand curve or supply curve. So just want to have a high level understanding of what you are doing.
So what we want to do is to find a price such that the people here, they would have incentive to, in the end, implement what the market want them to do. That's a bit the idea. So for example, if you announce a price of 15 euro and that's stop here,
Yeah.
well, D would likely not be willing to produce anything, right?
So you want to give a price signal so that C and D will be willing to kind of submit their kind of bids in that situation, right?
Exactly, yeah. That's a bit the idea. Yeah.
Can you have multiple prices?
Yes, so in practice, so it's a good point. So typically you would have, so the idea here, I'm trying to find a uniform price. Now, because there is no equilibrium, in the end, people would typically do some side payments, right? So some of the people, for example, would be losing money, then the auctioneer would give side payments to them, which can be viewed as having multiple prices in the end, yes. The thing is that we would like these different prices to be maybe as low as possible, because having multiple price and discriminatory payment like that can impair a bit the transparency of the markets and these kind of things. So that's the idea.
This is, I mean, are you primarily applying this to the day-ahead market in Europe, or are you also considering of like imbalanced markets? Because I can see this more being.
This is more the day-ahead market.
Okay.
Yes, yeah. Yeah, no, good point. No, so that's mostly the day-ahead market because that's the primary place where you really encounter this kind of non-convexities. Yeah. Yes.
Why are we considering anything less than the 25? Because D wouldn't be like,
Anything less than 15, you mean, or
no, 25,
like something in between the,
why are we considering anything less than 25? If D is only willing to, if their marginal cost is 25, then they wouldn't bid for anything less.
correct. So what you were saying is that this last price should be the one that we pick.
I'm saying the other two, it doesn't, maybe you'll show us, but the other two don't seem like an option.
I see, yeah, that's a good point. So one option would be, so let me maybe go through the next few slides and then you tell me if you are convinced. Okay. So I think the main message here is when you go through an example like that and you try to analyze that, I think there are mainly two concepts that emerge from these discussions. And these are in fact the two main concepts that have been used in the literature to analyze this problem. And these are the concept of lost opportunity cost and revenue shortfall. So lost opportunity cost, and again, just to make sure that you follow me. So these two concepts, the goal is really to measure when you have a price and an allocation, how inconsistent they are with one another or what kind of issue they resulted in. Okay. We just try to measure this. So lost opportunity cost, mathematically, that would be defined as follows. So this is the difference between the maximum profit that an agent would make given the price if he sells schedule, minus the as cleared profits, so the profit that he makes if he implements the dispatch clear in the market, right? So this loss opportunity cost, it really measures how much the price does support the solution and how much someone would have instead some incentives to self-schedule. That's really what these loss opportunity costs are measuring.
What is the second part? Is it the equilibrium price, like cleared profit is?
This clear profit, yeah, that would be the cleared allocation times the cleared price. So the money that he would make if he just follows the market dispatch, yeah. So these are the loss opportunity costs. Then the second concept is the one of revenue shortfall. So that's just the notion of how much does the price enable the market participant to break even, or how much additional payment should we provide to them in order for them to break even, right? So this, if you have these two concepts, then I think there are three natural.
Can I just ask,
Yes.
so I'm kind of thinking about generators in this context, but do those terms apply to consumers as well?
Yes, correct. So actually in the model, in the paper, we have inelastic consumers. That's just an assumption. In practice, I think you have very inelastic consumers in general in electricity markets.
Yeah.
But yes, you can totally extend this concept to consumers as well. Yeah. So when you have these two concepts, I think, so you have an infinite amount of possible price that you could choose, but I think you have really three main candidates that naturally emerge from that. The first candidate is marginal pricing. So that's very well used in economics. In convex settings, it works pretty well. So in this, you could say, well, let's just apply marginal pricing to our example here. So in the example, marginal pricing would be, in this case, 20 euros. Maybe it's not that intuitive, but so the idea is when you fix when you're at the optimal dispatch, what is the cost of increasing or decreasing a little bit the demand? Well, so that is at the optimal dispatch, or when you fix your integers, how can you change a little bit at the margin? And the answer is that it's B here who is the guy at the margin. And so he's setting the marginal price, right? Mathematically, that would just be, so mathematically, I guess, maybe you'll see that, but so your primary problem before was non-convex. So you don't have strong duality and your price would typically be understood as dual variables, right? So the main problem of non-convexity is that you lose this non-convexity stuff. So this pricing scheme, there are often some form of convex relaxation or restriction of your primary problem. And so marginal pricing in particular, mathematically, if you want to define it, it would be you take the primary problem number one that I showed before, you fix the integers to the optimal. So that is a convex restriction of your first problem. And then you take the price as the dual variable associated to the market clearing constraint. Yes.
So in this example, if I increase the demand of B, then I mean, would the optimal dispatch change at all? Because I'm already not clearing all of the demand of B. I guess it would only change at some point if B was consuming a lot more, so that it becomes attractive to dispatch C.
Yeah, but so I think the way, if you want to see it graphically, the way to view it is, so if you have an inelastic demand.
Yeah.
And that's you change of an epsilon.
Yes.
So basically here, so when you reject C and you clear D,
Yes.
in the end you have a vertical line that goes from minus infinity to here.
Yes.
And if you want to change a little bit your demand, like you had an inelastic demand of epsilon
Yes.
plus or minus, it would change like that. And so it's B that would be asked to consume a little less or a little more. So it would be setting the price. Graphically, that's the way to view it.
But D can already not supply everything that B wants to consume, right?
Correct. So if you would include an inelastic demand of epsilon, the guy that will actually change is B because he will consume a little less then.
And so then
And
the
so you
price
set the
of that
price.
is the 20. I see.
Exactly,
Okay,
yeah.
got it. Okay, thank you.
Does that
Yeah, that makes
make
sense.
sense?
Yeah, thank you.
Okay, great. Marginal pricing, first option. Second option, where you can say, we have just seen lost opportunity cost. Why not just say, let's take the price that minimizes this lost opportunity cost? Right. Yeah, maybe something I should have said before, but so one thing I think one thing to view here is that the revenue shortfall, I think you should view that as one particular type of lost opportunity cost. So the revenue shortfall intuitively, this is a lost opportunity. It's a lost opportunity cost where the lost opportunity is the guy that has revenue shortfall would like to self-schedule at zero. He would like to exit the market. So revenue shortfall is a certain part of lost opportunity cost. So when you want the price that minimize total loss opportunity cost here, well, in this case, it would be 15 euros per megawatt hour because the total loss opportunity cost is 1050, which is lower than in these two other cases. Mathematically, the way, so this has been called convexive pricing. And because mathematically, the way to actually compute that is you have your Proman problem and you take the convexity of your production sets. That's the way to compute that. And you can prove that when you do this, then your convexive price, they indeed minimize your loss opportunity cost. And then I guess you all see me coming with this, but so the last third option would be then another idea would be let's just take the price that minimize revenue shortfall instead of minimizing loss opportunity cost. This has received a lot of names in the literature. Here I choose the name minimal make-whole payment pricing that was used in some papers. And in this example, that would be the price, the 25 euro per megawatt hour. Okay. And mathematically, I think I need to hurry a bit, so I will not actually explain that, but you have a way to define that mathematically, where you can establish that these are indeed then the price that minimize make-whole payments or revenue shortfall. So to sum up, what we have seen so far, so we have this lost opportunity cost and revenue shortfall metrics that can measure how far we stand from an equilibrium or how bad is an allocation and price goes together. And we have three main pricing candidates, which again, I think there would be an infinite number of candidates, but I really think these are the three kind of cardinal points that you want to keep in mind when approaching this problem. And so these are marginal pricing, convexive pricing, and minimal make-whole payment pricing. So convexive pricing is the one that minimizes LOC. Minimal make-whole payment pricing is the one that minimizes revenue shortfall or make-whole payments. And then maybe let me just say very quickly, yeah, that if you think about it mathematically, so we have seen the definition in the previous slides. So computationally speaking, minimal make-whole payments and marginal pricing, these are very straightforward problem to solve, right? It's just a small convex problem that you can send to Gurobi, Cplex, or your favorite solver, and that would be very straightforward to calculate. The convexive price is the one that is really a bit tricky. And the reason is that computing the convexive of a set is actually not straightforward. So you could derive some tight formulation, for example, but that typically works only for relatively simple model. Or you can define some more general algorithm, but that's not obvious. The good news is actually, yeah, my first research in my PhD was trying to develop an algorithm that solved that efficiently. And so there are actually ways now to compute this convexive price for relatively big instances. So I don't have the time to go through these computational issues, but just to give you an order of magnitude, in the auction data set that we will see in a minute, like the biggest auction data set is solved on my personal 10 years old computer in like 2-3 minutes or something like that. So you can solve relatively big instance and without any fancy implementation, like without parallel computing or things like that. So you can solve relatively big instance on a personal laptop. So it has become kind of feasible to compute convection prices for relatively elaborated.
What's the type of optimization problem you solve in that case? Is it
In the data sets, it's a unit commitment model. No, you mean what I solve in this algorithm?
Yes, exactly.
Okay, so when you want to compute the convection of a set in the problem, one way would be, for example, a dense equal decomposition or column generation algorithm. Another way is you can actually show that this is equivalent to solving a Lagrangian relaxation. And so in this algorithm, I'm solving the Lagrangian relaxation directly. So mathematically, so this is a convex but non-smooth problem, right? It's a piecewise linear function. And what you do, you cannot send that to simplex of Gurubi because you don't have full structure of your problem. What you can do is just evaluate. So you have a first order oracle. So you can evaluate subgradients and value function at a certain point. And then you need to have an iterative algorithm that uses this subgradient information to find the optimal. Yeah. And the way it works is the so-called level method that we have used in this paper. Yeah. I guess we can talk more offline after that if you are interested. Yeah. All right. So let me jump now into numerical result. I have 15 minutes. I guess that will be sufficient. So in order to, so we have our 3 pricing candidates, and in order to cross compare them, as I said in the paper, we go into more theoretical inquiry. Here I jump that and I'll directly go to this numerical result, where we have basically compared these pricing schemes on 2 different auction data sets. So the first data set, later called the third data set, is one that includes 1,000 power units. But the main limitation is that it has no network. Since the network is arguably an important feature of our electricity markets, we have also used another auction data set, which is later called the CWE dataset. This has 70 power units, so a little less than the other dataset, but it has a network of 30 billing zones. So that's also useful to understand, you know, what would happen in case where you have a network, which is arguably something quite important. Yeah. So the way we proceed is, for example, if you look at the CWE dataset, so we solve the primary problem. So we find the optimal dispatch and commitment instructions. We do that for actually, we have 12 load scenarios in this case. So we compute this primary problem, and then we've implemented our 3 pricing candidates and actually a little more. So in total, we have 6 pricing schemes that we analyze in the paper. So these are the columns here. And then for each of these prices, we compute the price, and we then compute the lost opportunity cost and the revenue shortfall, right? And we do that for the 12 scenarios, and this table shows the average final result. So in the paper, we do, we look at many different things. Here, let me just stress 5 main messages.
So ELMP, did you define that? Is that like a version of convexual pricing, basically?
So I've not defined it in the presentation, but ELMP, it's just an integer relaxation of your model.
Okay.
And indeed, that can be viewed as a kind of approximation of convexual pricing. Yes, indeed.
That's what they've done in MISO, I think, in the US.
Exactly. Yes. Yes.
Yeah.
Yep. Okay. So let me stress quickly 5 messages. So the first one is, if you look at the marginal pricing column, the lost opportunity cost and the revenue shortfall that you get here are, compared at least to the other candidates we will see later, are relatively higher. And this is a bit expected. So I think the intuition is just that since marginal pricing simply ignores all the non-convex costs, these are not reflected in the price signal, and therefore it can lead to relatively poor incentives of market participants, which is reflected here. And compared to that, convection pricing improves this incentive. It more or less cut by 10 on this data set, the lost opportunity cost of your market participants. So this is kind of expected, right? This is the approach that minimizes LOC, so it indeed leads to a significant improvement of lost opportunity cost. What is interesting to observe, however, is what happens to the different market participants individually. So the total lost opportunity cost in the end, that's not, that's something that reflects incentives of individual market participants. And so you want to understand what are the kind of incentives that they are facing individually. And so on the box plot here, what I'm showing is the lost opportunity cost borne by each individual market participant in this case, and I'm comparing convex pricing with marginal pricing. And what you see is that it's not only that in total there is less lost opportunity cost, it's also that the distribution of these among participants is such that each individual market participant face actually a much lower lost opportunity cost. I think that that's kind of important because if you look at the dots over here, and actually, yeah, when I did this plot, for some reason I truncated the graph, but there are some more dots over there. So when you look at these dots there, these are market participants that individually have tens of thousands of dollar or euro to deviate from, to self-schedule basically. And so these guys that have huge opportunity to self-schedule are really the one that in the end matters, the stability of your dispatch instructions in your market. Let me skip that and just, so that was CWE results. On the first data set, we basically observe similar kind of things where we have also a big improvement of the LOC with convex pricing. So the second, or actually the third message that I want to stress is another thing that we look in the paper is, okay, convex pricing minimize LOC, therefore improve lost opportunity cost in your market. Another question is what would happen if your market size grows? So what happened to these non-convexities and to the lost opportunity cost when you're in a market that becomes bigger and bigger? That's a bit the idea behind this question that you are asking. And so in order to answer this question, we have done the following experiment. So we just select 50 power plants in our FERC data set, and then we duplicate these power plants to build a market that is, the first row here would be a small market with 50 power plants and a certain load. And then we duplicate that. And so we create a bigger market and a bigger market and so on, from 50 power plants to 1,000 power units. And we scale up the load accordingly. Okay. So for each of these rows, what we do is that we simulate the optimal dispatch and commitment, and then we compute what would be convection price for each of these markets and what would be the marginal pricing. And we calculate the LOC. And the thing that you observe, which I think is interesting, is the following. So with convection pricing, if you look at the relative importance of LOC with respect to the market size, so this is just lost opportunity cost divided by total cost, you observe that this lost opportunity cost is smaller than marginal pricing. That's what we've seen in the previous slides. But what you also observe is that it actually tends towards zero when your market size increases. And remarkably, this is not the case for marginal pricing. So when here the market size increases, the relative importance of your lost opportunity cost remains the same. And let me maybe just conclude and then you'll ask a question. So remarkably, what is interesting here is that this phenomenon that we observe when we make this simulation, you can also formalize that mathematically. And the idea is you can show that with convection pricing, there is a bound on the total LOC that you can have in your market, a bound that I call gamma here in proposition 11. And this bond, it depends on the shape of your production set, so on how the non-convexities look like. But the bond does not depend on the number of market participants. So when your number of market participants grow, the bonds stay the same. And so the loss opportunity costs become relatively small compared to the market size. So you have a kind of the non-convexity smoothen out when the market grows. But that is true with convection pricing and not necessarily with marginal pricing. Well, that's a bit what we observe here. And you had a question.
Yeah, and it's exactly about this. So I'm not sure I understood correctly. Because we would expect, right, that the lost opportunity or that the importance of this indivisibility goes down as the market becomes more liquid, as there are more participants in the market.
Yes.
And so now I'm not sure I quote exactly. Did you say that the bound depends somehow on the number of plants that you have or not?
No, it depends on the shape of XG.
Yeah.
so the shape of your production set, so the non-convexities, how they look like, but it does not depend on the number of market participants.
But isn't that counterintuitive? Like, wouldn't we expect there to be less of a problem as you have more generators because it becomes more
Exactly. So the bonds stay the same, even if you multiply the number of market participants by 10 or 100. So that means the total LOC would be the same, while you would have a market with 100 more market participants.
The numerical results indicate that it actually drops a bit.
Yeah.
In the table there.
Yeah,
Although it goes a bit up and down, I guess.
but it's the
Oh, okay, you're concerned with this 2000.
Yeah.
Yeah, right.
At 11, I guess it goes.
Okay, yeah, so what you see is that it goes a bit down and then up and then down, so this is not monotonic. I think the importance of this is more the relative importance of LOC. So more or less here, you stay around 10,000 euro, let's say, of lost opportunity cost, while your market size is multiplied by 20. So that means that your LOC remains more or less the same, while actually you have a significantly bigger market. So this is the kind of smoothing out effect that we observe, yeah. Let me stress, because we have 7 minutes, so the last two messages, which are, I think, also relevant. So far we have mainly talked about LOC. So let's have a look at revenue shortfall. So the first thing that you observe is that convex pricing, although it minimizes the LOC, in the end leads to relatively small revenue shortfall that actually improve, results here compared to marginal pricing. And the intuition for that is exactly what I said before, that revenue shortfall should be viewed as a certain type of lost opportunity cost. So it's a lost opportunity cost where the lost opportunity is I would like to self-schedule at 0. And because these revenue shortfall are kind of a part of the lost opportunity cost, when you minimize lost opportunity cost, your revenue shortfall remains small. They remain contained because they are part of what is minimized in the end. But what is interesting to observe is that this is actually not true. So there is an asymmetry here, and it's not true the other way around. So when you minimize lost opportunity cost, revenue shortfall stays small. When instead you look at the approach here that try to minimize revenue shortfall, well, then the lost opportunity cost can explode. So that's a bit the asymmetry that we observe. And so maybe deserve a couple of more comments. So the first one here is that you see not one, but 3 different approaches that are called MMWP. The reason for that is actually, if you think about it, minimizing revenue shortfall is a very mild requirement in the sense that if you're in a case with inelastic load like that, making sure having a price such that everyone breaks even is super easy. You just take a very high price and everyone will break even. So if the only objective is I want to minimize revenue shortfall, there are actually many prices that can do the job. And that's why in the literature, you actually see different possible alternative way of meeting this objective of minimizing revenue shortfall. So in the paper, we compare these 3. And if you just look at the last column, which is actually the one that works the best in what we have tested, what you see is you have with convex pricing like 90 euros, so nothing, right, compared to the cost of your market of revenue shortfall. And if you want to go from 19 to 0, which is what you do here, you then increase of more than 14,000 euro the lost opportunity cost. And when you include the network, no, that's this one, that becomes even more dramatic, where by just reducing a little bit the revenue shortfall, you create millions of lost opportunity costs. So that is a bit, so all you minimizing the revenue shortfall, to me, it sounds like a reasonable target, when you just explain it. In the end, when you make this computation like that, you see that it can actually lead to very bad incentive for market participants to self-schedule and deviate from market dispatch instructions. So that was a bit what we learned from these simulations. And this is good timing. So that's the last slide. So to conclude, what we have seen is, so this problem of pricing non-convexities, that's a big debate for almost or a bit more than 20 years actually in the US. We have many different practices of how the ISO actually try to solve this issue. It's also a problem in the European market, and there have been recently some discussions to actually reform this rule in Europe. And as far as the European market is concerned, I think that marginal pricing, that could actually be a good upgrade, like compared to the current pricing rule. Both in terms of welfare and scalability, like algorithmic scalability of this pricing rule. However, I think that, yeah, European stakeholders, they might want to pay attention also to the fact that this rule has been used in the US and the ISO have tended to move away from that to implement something else. And so you might want in Europe to directly implement something better than that as well. And what we have seen is convection pricing that leads to significant improvement of incentive for the market participant while making sure that the revenue shortfall remain contained. And we see that under this rule, you have also this property of having lost opportunity because that will become relatively small when your markets increase relatively to your market size. And finally, we saw that the minimal make-whole payment pricing or minimizing the revenue shortfall, although it sounds like a good idea, can lead to actually very high and unbearable lost opportunity costs. Yeah, and that's it. So thank you very much. And I guess time is up, but I'm here. So if there is any question, I'm happy to take them. Yeah.
Oh, yeah, on that conclusion slide, you said that marginal pricing would be an upgrade compared to the current rule. What is exactly the current rule?